Buenas tardes, en 5 minutos empezamos con la transmisión. Esto es para comprobar nomás que estemos saliendo bien al aire. Buenas tardes, en 5 minutos empezamos con la transmisión. Esto es para comprobar nomás que estemos saliendo bien al aire. En 3 minutos comenzamos.
Buenas noches, amigas y amigos. Bienvenidos una vez más a Astronomía en Cuarentena, nuestro ciclo de actividades online a través de nuestro canal en YouTube. Un desafío en la difusión de astronomía de calidad del que estamos muy orgullosos. Y orgullo es la palabra del día porque hoy presentamos nada más y nada menos que al doctor Anthony Cook. Tony es nuestro mentor en la observación lunar. Podemos decir que aprendimos a observar la Luna de manera rigurosa gracias al programa de verificación y eliminación de reportes históricos de fenómenos lunares transitorios que el Dr. Cook dirige, englobando a la British Astronomical Association, BAA, a la Association of Lunar and Planetary Observers, ALPO, y a la Aberyswyth University de Gales, espero haberlo pronunciado bien. La conferencia será un viaje fascinante por la historia de estos controvertidos eventos de corta duración que se llaman fenómenos lunares transitorios. Veremos los casos más importantes, casos que han sido desestimados, estadísticas y teorías sobre su probable causa, información útil para reconocer brillos y oscurecimientos en la superficie lunar, que a menudo han sido confundidos con fenómenos lunares transitorios, y el moderno estudio de reportes históricos para depurar los catálogos de falsos fenómenos lunares transitorios, a través de la observación en condiciones de idéntica iluminación de la superficie lunar respecto a la observación original realizada por el observador que lo reportó. Estudio del que participamos hace ya más de 5 años. Esperamos que esta conferencia, que quedará como todas las demás actividades de Astronomía en Cuarentena en nuestro canal en YouTube, sirva además para sumar participantes a este muy interesante programa, uno de los más importantes a nivel de astronomía pro-am que conocemos que existan. Las preguntas que se quieren realizar deberán ser enviadas por el chat de YouTube o por el email de la Sociedad Lunar Argentina @gmail.com. Por obvias razones de lejanía, Anthony Cook no está presente, sino que nos ha enviado esta charla, pero pueden ser enviadas al mail o al chat y se las responderemos. Él también, al finalizar la conferencia, muestra su email y está deseoso de recibir preguntas. Bueno, un par de cuestiones. Una, como internet en tiempo de cuarentena es una lotería, si se llega a cortar la transmisión, por favor manténgase conectados por unos minutos, así nos dan tiempo a reanudar la transmisión. ¿Qué le va a hacer? Así está internet en tiempo de cuarentena. Esta charla también cuenta con certificados de participación, así que si el que los quiera recibir puede pedirlos al mail que ya dijimos, sociedadlunarargentina@gmail.com, y por ahí también se lo enviaremos. Bueno, por último, el último aviso parroquial. No se olvide, mañana desde las 19 nos sumaremos a la International Observe the Moon Night de la NASA, con una transmisión de la superficie lunar en directo. Vamos a contar qué es lo que se está observando en luna creciente desde la superficie de la Luna. Esperemos que se pueda, porque está anticipado mal tiempo para mañana. Veremos con qué la reemplazamos o si la postergamos, pero de todas maneras se van a enterar por este canal. Bueno, amigas y amigos, como siempre, gracias por estar y los dejo con la conferencia de Anthony Cook.
Greetings to the SLA from the British Astronomical Association and the Association of Lunar and Planetary Observers. My name is Tony Cook. This talk is about transient lunar phenomena. Now, there have been over 3,000 of these reports over the last few centuries where people have seen curious, very short-term glows on the moon or colours. And many of these have been catalogued in this NASA catalogue over here, Lunar Transient Phenomena Catalogue, produced by Winifred Cameron back in 1978. We'll be covering today a few historical examples, the kinds of mistakes people make when they look at the moon and misidentify TLPs. We'll take a look at the statistics of TLPs, discuss some of the theories, and then finally encourage you to make observations of the moon which can be used to actually disprove a lot of these TLPs and perhaps highlight ones which we can't disprove. One of the earliest TLP reports came out of Canterbury in southeast England, and it concerned some people who were sitting down watching the moon sink towards the horizon in its crescent phase, as you can see from this image up here, and all of a sudden they saw some interesting effect on the top right hand corner of the crescent, as is depicted in this artistic drawing made many centuries later, so we don't really know it's accurate, but they describe in their time how they saw the crescent split and flaming coal-like things appear from there, and it's quite poetic, some of the descriptions which they made. We're not absolutely too sure what they saw, but nevertheless it was written down by Gervase of Canterbury, and we now have this as a TLP report. Astronomers have looked for a possible impact crater. They thought maybe this was the result of a meteorite, a very big meteorite hitting the moon just over the far side, and they have in fact found this crater here. It's called Giordano Bruno. It's 22 kilometers across, and for many years they suspected that was the crater which formed when perhaps a meteorite hit the moon, and that's what the monks saw. Now, recent analysis of the images and modelling on the computer suggests that this is actually quite unlikely. Although this crater is geologically very, very young, just a few tens of millions of years old, it's way, way too old for the monks to have seen. And also, if a crater of that size had formed from a meteorite striking the moon, the debris thrown out would have caused a massive meteor shower here on the Earth, and there's no record of that being seen in the year 1178, so we're not too sure what they saw. There are a couple of other observations which we now think are possibly impact related, meteorites striking the moon. The first one over here was a sketch made of the crater Plato by Thornton, and this was just towards the actually at the end of the Second World War, and he recorded seeing a very bright flash of light which resembled to his eyes what he remembered of anti-aircraft fire from firing sort of things up at German aircraft flying over London when they were dropping bombs and so on. He described it as a sort of orangey type of glow, and he shows you the position over here. We have another one over here. This is an actual photograph by an American Dr. Leon Stewart from Kansas, and this is quite an interesting story. He was testing out a new telescope camera system, and he was using photographic plates, and he tried different exposures. They were all very unsuccessful, so he tried modifying things, and on this occasion he was about to put a photographic plate in, and he noticed on the ground screen which you use for focusing the camera on the telescope, there was a bright spot. You can see it over here. Now this of course could have been a reflection inside this telescope, so what he did was to move the telescope about, and that spot stayed exactly on the same place on the moon. So he pressed ahead, he took a photograph, and he took the photographic plate inside, developed it, and sure and behold, that spot was there. He came back out to see if it was still there, and it had gone by that time. Now we think both of these are probably not TLPs, but impacts on the moon from meteorites striking the moon's surface. Pretty big ones, because they produce a spot of light visible as it cools over many, many seconds. Rolling on to 1958, and we come to another rather important milestone in transient lunar phenomenon history, and this is an observation by the Russian astronomer Kozyrev on November the 3rd, 1958. He was using a very big telescope down in the Crimea, the Crimean Astrophysical Observatory, and he was testing out the spectroscope on the moon for use on Mars a bit later, and he put the spectroscopic slit, because that's how spectroscopes work, across the central peak in Alphonsus, and this doesn't work in real time. You have to take the photographic plate away, develop it, and come back. But he noticed that there were some spectral lines showing up. As you can see here, we have 3 sets of spectra at different times, and he detected some emission lines there, which he identified as being due to molecular bands from C2, that's 2 carbon atoms together. These are referred to as swan bands, and they often show up in cometary spectra. Now, although a lot of people study the spectrographic plates which were taken, they couldn't disprove the fact that he had recorded these particular lines. There was a little bit of discussion later saying it wasn't so certain that they were due to C2, these swan bands, and they might be due to some other chemicals, elements or molecules on the moon, still yet to be identified. That was the kind of final conclusion by critics of this. But it was nevertheless a fairly compelling case for a transient lunar phenomena, and it kick-started a lot of observing of the moon, looking for other types of TLP. Another rather compelling case was observed in 1963 from Flagstaff, Arizona at Lowell Observatory. Now, around that time, the United States Army and Aeronautical Service were making maps of the moon because you had the Apollo missions coming up, and they needed as accurate as possible charts of the moon's surface to help them navigate and land in the right place. They didn't know where they were going to land in 1963 because that had to wait till 1969, but they needed some really good maps. So they got some really expert cartographers. You've got 2 of them here. Greenacre was the one who was organising the mapping campaign, and Barr was his assistant. And they weren't terribly interested in TLP. They had heard about them, but they were not interested in seeing them. They were there to map the moon. Now, on the night of 1963, October the 30th, between 1:50 and 5 minutes past 2 in the morning, using this great big 24-inch Clark refracting telescope, they noticed some red glows on the moon. Now, this is a sketch map which was made afterwards, and they showed you the areas where they saw them. There were a couple of red spots over here, and then a little bit later they had this reddish glow over here. Now, being a refracting telescope, you can get things like chromatic aberration effects. That's due to false colour due to the optics of the telescope. Now, to get around that, they used a yellow filter which minimises that quite a bit. You can also get colours produced on the moon when the moon is low down. Now, it was reasonably high up. I think it was rising, but again, you get colours in certain places on the edges of bright features, and these colours were not where you would expect these false colours from what we call atmospheric spectral dispersion. Now, one of the things we do in the BA and ALPO is to get observers to look at the moon under exactly the same observing conditions, the same illumination as the original observer saw. And this is a picture taken from Bevieu and Smith over in Spain, showing the crater Aristarchus. It's a colour image, and the reason why we got them to do this, Bevieu and Smith and other observers, to see if there's any natural colour on the moon which could produce the reddish glows, apparent reddish glows where those features are, and there's just no way you can do that. We also added false atmospheric spectral dispersion colour on there, and chromatic aberration. Again, we cannot replicate where Greenacre and Barr saw those reddish glows in 1963, so this remains a bit of a puzzle. You have another example of a transient lunar phenomena, one which we've been trying to see again, but it hasn't recurred. On several occasions, observers have seen in this flat floor crater over here, which doesn't have a central peak, and it's confirmed by lunar orbiter images and lunar reconnaissance orbiter images. There is no central peak there. Nevertheless, we have sketches showing what looks like a bit of highland poking out of shadow. Here's another example. This is by Bartlett. This is by Walter Haas over here. This is by H.P. Wilkins. This is by Raffaele Lena. This is by Harold Hill, a noted TLP skeptic. He's drawn a white spot there. This is by Peter Grego. It's slightly further down there. And this is by V.A. Fursoff. There should not be a central peak there, but nevertheless, over a certain range of longitudes, or if you like, altitudes of the sun above the horizon on the moon, people have seen a central peak. We've tried time and time again to replicate this, and so far, despite the help of the SLA and other organisations, we haven't been able to get something which looks similar. So this is a bit of a puzzle. Now, if you're thinking that TLP are just confined to visual observers of the past, this is not the case. Here's an example by the famous French astronomer Dollfus, who in 1993 was using a CCD camera to do polarimetry study of the moon. That's through polarized light. And he noticed two things. By the way, this is a 1 meter diameter telescope from Woodland Observatory. And he noticed two things. There was a bright area near the central peak of this crater called Langrenus. And secondly, when he produced a polarization map image, there was an anomaly there which he had not seen on any other occasions, and he could not explain easily. It could have been some form of highly unlikely specular reflection on the moon. That's like you get light reflecting off a mirror, which can't be the case. Or he suspected there was a dust cloud above the surface. Now, although we haven't been able to investigate the polarization aspect, we did manage to get some repeat illumination images produced, and this is one of them over here, you can see. Now, in order to compare that with the white light image which Dollfus took, which was at a lower resolution, we have to blur the image, which you can see here. That is the repeat illumination image which has been blurred, and if you compare that with the Dollfus image, and I've adjusted them so they overlap, you can see that it looks pretty much the same. So in terms of this observation made in 1993, we don't see any difference between the white light appearance in 1993 and the appearance under the same illumination conditions in 2016. So we think that aspect of that TLP is false, but nevertheless some polarization anomaly was seen there, and it was recorded on the CCD, so that is unusual. Right, I've shown you some historical examples of TLP, and there are many of them. There's like about 3,000 altogether. Some are well documented, some are less so. It's important to get across to new observers and to existing observers that mistakes can be made, and here's an example. Back in 1973, this astronomer Bartlett from Baltimore was observing the crater Ptolemaeus, and I will quote exactly, I'll read this word for word. He said, "A large oval bright area between the centre and the south wall was seen, though the floor was in shadow, and it looked like a feeble surface glow." Now that's come out of the Cameron catalogue, which was in the very first title page, and that's all we get. It's a TLP report. Now let's investigate this. This is a sequence I took a long time ago, again under similar illumination, and it shows just a few minutes apart sunlight reaching the floor of the crater, and gradually you can see more and more of the floor of the crater. It looks like a feeble glow. So that tallies with what that observer saw, and we now know that that was not a TLP. They should have followed through their observation over a few more minutes, and they would have seen all these shadow spires form across the floor as the sun rises above the horizon, and it's just a normal appearance of the crater. So another common mistake is due to colour effects from the Earth's atmosphere on the moon and from chromatic aberration in the telescope optics. And remember the Greenacre and Barr observation, they were well aware of that. That's why they used a yellow filter, and they checked other craters to see if they could see a similar effect, but couldn't. But this shows you, this has been generated on a computer, and it shows a crater over here, and as the moon gets closer to the horizon, the red light and blue light components get refracted by the Earth's atmosphere by different amounts, and you get colour fringes appearing on contrasty areas or edges, and they get stronger and stronger as the moon gets towards the horizon. So you can see we've got a lot more blue over here than we had on this one, and a lot more red on that dark area. So it primarily affects contrasty areas, but it can also affect gradients. Here's a grayscale, it's a gradient going from dark to bright. but depending upon the way the refraction in the Earth's atmosphere is dispersing the colours, it can cast a bit of a bluish tinge onto a gradient or a reddish tinge, which can give floors of craters false colours and surprise even expert astronomers. This is chromatic aberration. It's a radial effect out usually from the centre of the optical axis of the telescope, where you will get very little chromatic aberration, but towards the edges the colours get stronger and more dispersed. Now, the way to get around this, to avoid mistakes, is to check neighbouring craters. Do they show similar effects? If they do, it's a false effect. Now, if you're still uncertain about whether colours on the moon are due to chromatic aberration or atmospheric spectral dispersion, the surefire way to do it is to use some filters. So we can use a red filter and a blue filter. And we have an example here of this crater. That's a picture for the red filter, that's a picture for the blue filter. And you can probably see immediately that this little crater over here is, in red light, it's dullish, but in blue light, it's brightish. Now, if you can alternate between red and blue and do it fairly quickly, if there is any colour on the moon, then which isn't due to chromatic aberration or atmospheric spectral dispersion, then that particular area will be blinking on and off. And that's the principle of this device called a moon blink, which was used in the 1960s and 1970s and 1980s by visual observers. Now, these days we have things like colour cameras, colour webcams, and they're also pretty good at picking up colours. You take a picture in colour and then you just boost the colour saturation. Any colour there you will see fairly easily. So that's a picture through red and through blue, and as you can see, there was a change in there. Even with CCD cameras, you have to be careful, particularly the colour ones, the ones which take pictures straight away for you. If you looked at the camera chip, this is CMOS or CCD, under a microscope, you'll see it's got lots of little tiny pixels on it, and they have colour filters placed over them: blue, green, green, red, and so on. And that's how they take the pictures. They're combined inside the electronics or inside the computer to produce a colour image for you. But having a matrix like that can cause problems. For example, if we had a bright line on the moon's surface, let's say a ridge running across there, if it happens to lie across the green, primarily the green pixels, it's going to come up with a green colour and look a little bit odd. If it was over the green and blue, it would have a kind of turquoise type colour. So be careful about using colour images. Move the image around and you'll find that if the colour changes on a particular feature, then it's almost certainly due to this BAA type arrangement of colour filters on the camera surface. Another thing you've got to work out for, if you're not using a BAA type camera, if you're using a camera which does just black and white, and you put a red filter, a green filter, and a blue filter over there, if there are dust marks on those filters, they will produce this diffraction effect, and you can get strange things like this appearing on your composite color image. So the best way to check for those is to look at the red, green and blue channels, and if you see what we call donut-like rings, American type donuts, then it's diffraction effects of dust particles. People can even be caught out by natural colours on the moon's surface. Now, to you and I, most of the moon is just pretty much boring grey. But with web cameras and people with good colour sensitivities in their eyes, some people are very blue sensitive in their eyes. They can see blue colours or perhaps even a little bit into the ultraviolet. Other people, like me, I'm actually pretty good at seeing into the near infrared a little bit beyond what normal people can see. There are some colours on the moon. You can see here Aristarchus crater. This is a colour webcam image, and it's got a bit of a bluish, turquoise bluish tinge to it. Here's some other examples. You get fresh impact craters, geologically speaking. I mean, this is the top right hand corner, the northeast end of the Alpine Valley on the moon, and there's a little crater there, and it's basically punctured through beneath the surface and thrown up some of the underlying material, which has a slight bluish cast to it. So although most of the area around there is a kind of browny, dull brown type colour, that stands out as quite a strong turquoise blue. You need really good resolution, as you can see here, in order to pick that up. So just watch out. Some features on the moon do have natural surface colour, and that has caught people out in the past. One thing which has caught observers out in the past is judging how bright a feature is. Sometimes you'll get TLP reports where they say Aristarchus is looking incredibly bright tonight, but as that's a visual report, what do they actually mean? It's all subjective. And even if you have CCD images, sometimes features will look bright and sometimes they will look dull depending upon the resolution. And this is an example here. This is a crater on the moon, and that looks like it's the brightest feature over there. Certainly stronger than anything and brighter than anything else you can see. But let's try to improve the resolution a bit. Okay, now that crater is starting to look equally, or perhaps a little bit dimmer than that. But that is still fairly bright compared to other little points on the moon. And let's increase the resolution still. Now that crater's looking the brightest, and perhaps that's the next brightest, and that one over there. And we go to full resolution. As you can see, you've got to be really careful. If you are comparing the brightness of one crater, if you are saying crater's looking really bright, please compare it to another crater and definitely take a photograph so we can replicate this and do repeat illumination in future. That's how we can avoid mistakes like this occurring. Here's an example of where we have a TLP which crops up fairly regularly for a certain range of phase angles on the moon, and it's a bright spot on the northwest corner of Mare Crisium. And all it is basically a part of a slope of a mountain which has got a very small ray crater on it, and at those range of angles it reflects the light fairly strongly, and we get what looks like a star-like point. It's particularly strong when people use low magnification as opposed to high magnification. At high magnifications it looks like a little tiny crater, but at low magnifications it looks very star-like. There's other examples of this. If you look at Mons Pico and Mons Piton, which are more towards the centre and north part of the moon, at sunrise, again, they reflect, the slopes of those reflect light fairly strongly, and at low magnifications they can look almost star-like. And under bad observing conditions, when the moon's low, you can get lots of little colours dancing around those, which looks very spectacular, but they are not TLP. So please be on the lookout for these things and try using a higher magnification to see what is actually there rather than just saying it's star-like. In the modern era with CCD cameras, we can also get TLP reports cropping up, and they usually are caused by internal reflections off of the eyepiece draw tube which the camera's on, or internal reflection if people are using a Barlow lens to magnify the image a little bit, which is a legitimate thing to do. It's perfectly okay, but sometimes at certain positions between the Barlow and the lens and the camera you can get internal reflections. So here's some examples. So this one actually made into a German newspaper. Somebody said they thought they had photographed an explosion on the moon, whereas in fact again it's just this reflection off of an eyepiece draw tube. Now the way to check for this is to move the moon around, and if it stays static on the moon it is a genuine impact, I guess. But if it stays static in the field of view but the moon changes in position, it's internal reflections. Here's another example over here. This was published in the Sky and Telescope. It's in the crater Pitiscus. We don't know if this is a TLP or internal reflection because it was not really followed up. It hasn't been seen again, but I suspect strongly that that may have been due to internal reflections inside a Barlow lens. Although the observer did say that they saw it visually as well, but if it was through the camera looking through the Barlow lens, yeah, it could be internal reflections. It did move around a bit on the moon's surface, which is kind of would suggest it might be due to optics rather than really on the moon. But just be on the lookout for these things, please. Now, if TLP are due to some phenomena on the moon's surface involving hot material or spectral emission of light, the best chance of seeing it is actually on the night side of the moon, because there the light reaching the moon's surface comes from the Earth. It's reflected light from the Earth, but it's about 7,000 times fainter than the light you get from the direct sunlight, which you see at full moon time. So it's a good place to look for TLP. You don't need much energy to produce a glow, which could be seen from the Earth. Indeed, most meteorite impacts have been seen on the night side of the moon because they're not swamped out by the glare from the day side. But the problem is, if you're looking visually, you're running on the limits of the human visual system, and you get a lot of noise there, which causes massive problems in interpretation of what you're seeing. Even CCD cameras and CMOS cameras, video cameras, are affected by noise. And it's not just that as well. Here's a couple of examples. Again, CCD images, ones I took. Aristarchus on the night side of the moon. You've got craters to compare it with here, which is really useful. So you've got Kepler, Copernicus. This is one day later, but look, Aristarchus has faded, so it must have been bright there. Well, actually, if you measure the brightness on the CCD image compared to the background, the brightness there compared to the background, you will find it has actually not faded. It's what we call a brightness gradient effect. I will demonstrate this on the next slide. It's something you need to be aware of. Okay, to illustrate the point, we have a couple of spots here. They could be Aristarchus crater, could be anything. And we've got a brightness gradient across here. Now, to you and to me, I think you'd say that one looks the brighter of the two. Okay? It does, doesn't it? Look, it's light grey, and that's a little bit of a darker grey. Okay, now let's take away those brightness gradients, and I'll ask you again, which of those two spots is brighter? That one or that one? They're now, to my eyes, they're equally bright. And this is the issue. If you've got a brightness gradient, and this applies to Earthshine because you've got the glare from the day side of the moon making that part of Earthshine bright, it's scattered light in the telescope optics, as opposed to the bit towards the limb of the moon in Earthshine, which looks darker, you're going to get a brightness gradient, and that can affect our interpretation of craters like Aristarchus and Earthshine. I'm sure this has caused a lot of problems in the past, where you get TLP reports, people saying Aristarchus is looking bright, whereas in fact it's due to this brightness gradient. The way to get around this is to use CCDs and to look at the background immediately adjacent to the feature which you're suspecting is bright, measure that, measure the brightness of the feature, and check it again on another night to see how it changes. With people looking for impact flashes on the moon with light sensitive cameras, or indeed looking at the day side of the moon, from time to time you're going to pick up flashes. Now let's talk about the impact flashes on the moon. These are very short duration, typically less than 1/10 of a second, and you get a lot more fainter ones than bright ones. But unfortunately you get a lot of little flashes anyway, caused by cosmic ray air showers, and here's some examples. So this is the day side of the moon, the night side. We've got a streak over there, which is due to a cosmic ray. Here's another one over here. In this case, the cosmic ray has split into a shower of particles, and two of those have been intercepted by the CCD. And there's another example over here. So the way around that, if you're looking for impact flashes on the moon, is to have two cameras, one on different telescopes, perhaps geographically separated, to avoid sun glint from satellites. But always have two separate observations. That way you can rule out these radiation events. Even on the day side, if you're looking, you can get little flashes of light sometimes. For example, you've got a small bright ray crater, but it's very, very small, almost point-like Most of the time you won't see it because the atmosphere is blurry, but if you get a very brief sharp moment of good atmospheric conditions, it can brighten up and flash into view for a fraction of a second, and that can look like a flash. So the way to solve that is just to keep on looking, and if it happens again a few seconds later or minutes later, then you know it's probably due to the atmosphere causing that effect. You can even look at an atlas of the moon to see if there's a bright ray crater there, a small one, and that would solve your problem for you. Quite a few TLP reports come out described as greyness in shadows, and we've got a nice little image over here taken by Robert Spellman of the Griffith Observatory, and you can see Tycho here, created Tycho with a central peak, and you had a couple of what were referred to as spur-like points coming off over here. And I was very curious because it doesn't have any landforms there which can produce these, so that was a bit of a puzzle. But if you look carefully in other parts of the moon, a little bit overexposed, you can also see these spur-like features, and I refer to this as seeing flare. I'm not quite too sure on the mechanism behind this, but always check your images to see if what you suspect is unusual crops up somewhere else. You can even get grey inside shadows caused by glare from the illuminated area actually lighting up the floor, producing a greyness to a shadow. And to be absolutely sure, take a time sequence of pictures, monitor it over time to see if the effect changes. If it gets brighter and brighter, you can be pretty sure it's due to scattered light coming off of the sunlit rim. Try different eyepieces, different magnifications. Maybe you've got a bit of scattering inside your eyepiece. That's another good way of checking these things out. Now we move on to the statistics of TLP, and for those of you who don't like graphs, I apologise, but just please be patient. I will try to explain what it's about. Now, this is a plot showing you when people have seen TLP and what altitude the moon was above the horizon. Now, TLP come in different qualities. We have weight 1 TLPs, which are made by inexperienced observers, so that's why they're classed as weight 1s. Weight 2s and 3s are by experienced observers, but there was no other observer observing independently to confirm them. And weights 4 and 5s are where it has been confirmed by other observers, or they were using some scientific bit of equipment which you cannot disagree with its results. So as you can imagine, there's a lot of weight 1s because a lot of inexperienced observers out there are reporting things. Oh, we also include over here non-TLPs as a control to show you what distribution we would expect to see. You'll see this in a lot of the other graphs. So again, this is the altitude of the moon. Now, when it's close to 0, it means the moon's low on the horizon. You're looking for a lot of atmosphere, a lot of blurring effects, a lot of colours being produced. So pretty unreliable, any TLP reports down there. So this just shows you that most of the observations we have were made when the moon was at an altitude of about I'd say about sort of 35 degrees, 40 degrees above the horizon. Those are just routine observations that people haven't seen enough TLP. If you bring in weight 1s, well, yeah, that's a little bit lower. That's probably about 10 degrees lower. So that infers that perhaps these inexperienced observers are mistaking things like the Earth's atmosphere, blurring things or colours as TLPs. But as we get on to the more reliable ones, well, then it moves a little bit closer to the what you'd expect for most observations. So that has some quality suggestion in there to say that the more reliable weight 4 and 5s are indeed reliable. Okay, this shows you the geographical distribution of where TLP have been seen on the moon. Now, I don't want you to go out there and think, well, I'm going to see a TLP if I look at Aristarchus crater because it's got so many being seen there. I'd like you to follow through on our repeat illumination observations and not go off just concentrating on one particular feature. Plato looks fairly interesting too. Now, the size of these bubbles corresponds to the the number of TLPs which have been seen. So as you can see, yes, Aristarchus does have a lot of TLP. Plato is probably next, Proclus is probably next, and we've got Alphonsus and Gassendi. But do not go out expecting to see TLPs in those locations. They can occur pretty much anywhere on the moon. Some people said TLP occur around the edges of Mare areas, that's these dark areas, edges of basin rings, but from what I can see here, it's primarily bright ray craters. Usually they seem to be associated with. By the way, the colours refer to the weights, so the orange colours are the most reliable ones and the violets are the least reliable. Now that's all rather interesting, but where are people observing on the moon? If they've been told to go and look at Aristarchus, of course you're going to get a lot more observations there. Let's look and see in the next plot to see where people are observing on the moon in general. Okay, so this proves my point. People are attracted to bright ray craters, particularly when the sun is rising. They look very spectacular, but also to this ring formation over here. So what we really need to do, and I'm not going to show you here, you need to divide the number of observations of TLPs by the number of observations people have ever made of that crater, and then we get some sense as to whether the crater or whatever we are looking at on the moon has more TLPs than you would normally expect. Very important to take out observer bias, and that's what this plot is showing that we have. What about the times of the year that people observe? Could it be that, for example, certain meteor showers are producing effects on the moon's surface apart from impact flashes on the night side? Perhaps they're kicking up dust and causing certain areas to brighten up a little bit. Well, of course, it would have to be distributed randomly around the moon if it's a meteor shower, but are there any effects there? Well, this is on the x-axis over here. We've got the week since the start of the year, and this is what we've got here is a ratio. It's the number of TLP divided by the number of times people are observing the moon on those particular weeks. Again, I divided up into weight 1s, which are unreliable, and weight 5s, which are very reliable. It's kind of curious, they don't really convincingly line up with any meteor showers, although we've got some weight 1s over here. Remember, those are not very reliable, and if you look at the higher weight 1s, there's nothing to say they line up with meteor showers. What we do see is, for inexperienced observers, we do seem to see a bit of a peak around the summer months. Now, most of our observers, apart from you experts down in Argentina, are unfortunately in the northern hemisphere, and in the northern hemisphere during the middle of the year it's summer, and at that time during social hours, which is in the evening, we find the moon is very, very low on the horizon, particularly around August time. So what this is saying is we're getting a lot of TLP, more than we would normally expect during the summer months when the moon is low, and that's what's causing this apparent peak over here. If you look at the more reliable ones, the weights 4 and 5s, we don't have many of them, but again, there's no evidence of a strong peak showing here. So doing statistics on TLPs, we've got to be really careful about these social effects of the observers concerned. Now, the lady who produced the catalogue of TLPs from NASA in 1978, Winnie Cameron, and others before her, have considered the possibility that when the moon moves to the Earth's magneto tail, or crosses over into it, there could be some electrical effects on the surface which could, for example, charge dust particles and cause them to rise, and other effects. So that theory was popular for a while. What this tells us is if that was the case, you would expect to see around full moon time a lot more TLP. Now this is going to be normalized. It's the number of TLP divided by the number of routine observations, so people haven't seen a TLP for different weights. Weights 5s are reliable, weight 1s aren't. So if the theory about the moon crossing through the Earth's magnetotail, the magnetic tail of the Earth, where a lot of particles stream behind, was the case, then we would expect to see a strong peak there, even stronger in the high weight observations, but we're not seeing that. So that kind of disproves that theory. Even at where the moon crosses into the magnetotail, which is distributed over a few tens of degrees, we'd expect to see a couple of lobes either side, but we're not seeing that even in high quality data. What is curious though, a couple of things here is, firstly, we see when the moon is at a very thin crescent, we're getting a strong, even high quality data, we're getting strong numbers there. I'd like to explain that first of all. It's basically when people are seeing TLP in Earthshine. Now, think of this. If you go outside and look at the moon, if you see something exciting on the night side of the moon, you're going to record it, you're going to report it to me or whoever is keeping a record of these things. Take another night, you go outside, look at the moon, you don't see anything exciting, you're going to report it? No, you're just going to forget about it, because the night side of the moon is pretty, to the eye, it's pretty dark. It's not very exciting. You might see a few features there, but it's not as exciting as looking at the day side of the moon. So we've got an observational bias occurring there. So that's why we have peaks during Earthshine parts of the lunar phases. The second interesting thing, which I don't fully understand, is for the high weight observations, you can see as we move across there, there's a general trend gradually increasing. And that's after full moon. So what this is saying, there's more TLP in relation to ordinary observations where people don't see TLP occurring after full moon, like third quarter phase. I'm not too sure why this is. It may be perhaps the people who stay up really late are very determined, perhaps they're especially looking for TLP and they make mistakes, so we get a bias of observations there. Not too sure, but only by looking at statistics can we try to deduce what is going on. We're still trying to understand them, as you can see from these slides. Okay, here's another graph. I apologize for all the wiggly lines. The reason why they are wiggly is because I've joined all the points together, which is normally not a good thing to do, but it's the only way to avoid this looking like a complete mess. Now, one of the curious things is TLP seem to occur a lot more at sunrise or sunset on the moon, and this graph would seem to show that. You can see here the weight ones, a lot more of them are occurring at sunrise, about 0 degrees, and at other times they start to go down. Even the higher weight ones are around about a lot more common at sunrise. But if you look at what people are looking at on the moon and not seeing TLPs, you also see they will be looking at sunrise or indeed sunset. This is the altitude on the moon, so this is positive, the sun's above the horizon, this is below. So actually the reason why we're getting a lot of observations here, TLPs, is because at sunrise or indeed sunset the moon looks really spectacular on the terminator, and that's why we're getting that. So if you were to actually divide that into that, and I'll show you on the next slide what happens, you will see something somewhat different. By the way, we're getting a strong peak over here of TLP on the night side of the moon. Can you see it's happening around about 62 degrees when the sun is about, well, about 60 degrees, let's say, below the horizon. Now, strangely, or perhaps not strangely, the number of routine observations is very, very low there. And again, this is the effect I was describing earlier, Earthshine. If you look at the night side of the moon, you see something spectacular, report it. If you look at the night side of the moon and you don't see anything exciting, most observers will forget about it. They won't bother to write it down. So we have a depletion of these routine observations and no TLP, and that leads to a bias over there. So this should basically be ignored. By the way, this is caused by the crater Aristarchus. All these other ones are caused by other craters, but that is the crater Aristarchus, so don't trust that. So when we normalize the observations, by that I mean take the number of TLP on a particular solar altitude and divide it by the number of routine observations that people haven't seen in a TLP, you can take out those effects. This is not to do with solar altitude, it's the, if you like, it's the time of day on the moon, the local sun angle, the azimuth of the sun as seen from a particular point on the moon's surface. and when the sun is at 90 degrees it's rising, and when it's at 270 degrees it's setting. So you can see the bias there caused by these Earthshine observations, so ignore that. What is curious though is we've taken out that by dividing through by the number of routine observations, and no TOP have been seen. You see that terminator effect has gone right down, but what we are left with is there does seem to be a slight increase in TLP, particularly even stronger for the high weight ones towards local noon on the moon, when the sun is at its highest above the horizon. In other words, due south in the northern hemisphere and due north in the southern hemisphere. I just wanted to show you that. I've got a number of theories. I don't want to discuss them right now because I'm still testing them out. But I just wanted to show you that observations made, particularly TLP, and even more importantly, observations which don't show TLP, they all go into the statistical database and are producing some curious results. Okay, what about theories? I could spend hours and hours talking to you about the different theories which have been proposed and why they don't apply and so on, and ones which might have some advantages to them. This is just a flow diagram just to show some ideas of what might be going on. A lot of these are interrelated. So you've got volcanism down here. We don't think that's taking place. There are some features on the moon which are geologically very, very young, just a few million years, which indicates the volcanism isn't quite dead, but that isn't the same as saying that volcanism happened in the last century. It's highly improbable. But if it did, the effects we would see would be it could heat the surface and make it glow orange or red, a dull red, depending on how much heat is being released through the surface, particularly on the night side. If there was active volcanism, which again we don't think this is happening now, but you get fire fountains perhaps being produced, forming sort of a debris of material coming up. More likely, you can get much lower level type volcanism. Again, this is still pretty unlikely, but in terms of probability, if you had some gas emission coming out from way beneath the surface, perhaps from internal heating or some other sources, for example, quakes can release gas. If that happened on the night side, this gas might freeze out on the surface, and at sunrise, for a brief moment in time, you might see some frost on the surface. This has not been photographed yet. There are accounts of colour seen on the surface. For example, look at that Herodotus central peak thing, which it doesn't have a central peak, but from time to time people have seen it. That seems to happen shortly after sunrise. If gas is released, it may become ionized and start giving off emission lines and coloured glows. You need a lot of energy to do that. It's a rather tricky thing to do. Dust in it, the gas in itself can, if it's a particularly strong amount of gas coming out, it can levitate dust, and that can kick up some dust particles which can scatter light temporarily until the gas disperses. So the source of gas, or indeed dust, could be due to tectonics and quakes. Now, most of the quakes on the moon are what we call deep quakes. They are typically around about magnitude 1 or less, so you wouldn't really feel them. But very occasionally we can get quakes of about 3 or 4, and there is geological evidence that quakes of much stronger magnitudes, referred to as shallow quakes, do occur, perhaps up to 5 or 6 based upon the geology. Now, these are incredibly rare. You might just get about a handful per year over the entire moon. They're very localized, but those could release underground volatiles, hence a source of gas. You could potentially get mechanoluminescence, which here on the Earth you describe as earthquake lights. It might produce ball lightning. This is very speculative, so don't quote me on this, please. But anyway, shallow quakes do occur, and we might expect to see some effects being produced. You can also get quakes quakes being produced by impacts, and ejecta from clouds from very big impacts can potentially be seen moving across the surface. We do have a video from a Swiss observer which might infer that, but we only have one video. It was never confirmed. You can also get dust kicked up by landslides, but this again tends to be fairly localized and confined to the surface. One thing which has been proven in a laboratory and photographed from the lunar surface is dust particles on the night side at sunrise. They become charged by the solar wind flowing around the moon, and when they become charged they get opposite charges, repel, and can levitate above the surface. Now, although Apollo astronauts have seen from orbit glows on the horizon which they attributed to dust particles, we don't think that they normally can get up to tens of kilometers high. They're more likely just a few centimeters high, so we don't really understand the science behind this. We have conducted experiments in laboratories in a vacuum with lunar simulant soil with shadows, and we can there are YouTube videos showing dust particles on the shadows levitating and hopping across onto the bright side. But this again is only a few centimeters. We don't know if electrostatic levitation can explain TLP seen through Earth-based telescopes. Now, if it did, then you could have other interesting things. You could have me scattering, that sort of white cloud effect seen on the moon, a bit like what Dolphus was describing for that Langrenus observation. If the light's coming in, sunlight's coming into an angle, you might be able to get some absorption effects taking place, because the light coming into an angle goes through lots of dust particles, so you could get, depending on the size of the particles, you can get some reddening effects occurring. And in an electric field, if you have enough dust particles and they're highly charged, you can potentially get triboelectric discharge. That's little flashes of light. Now, these are all theories. We don't really have much evidence for a lot of these. We can see individual parts. We know dust particles levitate a few centimeters, but how this can be described on a larger scale to account for TLPs, we have no idea right now. Volcanism was on that list of explanations of TLP. I said it was very unlikely. I just wanted to show you a volcanic area. This is the part of the moon, the Mare Imbrium over here, and if we zoom in, you need to zoom in a lot using LROC, NASA LROC images. Keep on zooming in. Nothing very exciting so far. Oh, that's interesting. This is a D-shaped crater. It's not really a crater, it's called an inner formation. Let's zoom into that. Oh, interesting. Right. Now, according to geologists who've done crater counting on this formation, and also looking at the colour of it, which is a light blue, and both of the lines of evidence suggest that this is perhaps just a few tens of millions of years old. It's generally regarded to be a volcanic feature, and it just shows that volcanism on the moon hasn't died out entirely. But remember, it's tens of millions of years old, which, although geologically recent, doesn't mean to say active volcanism has happened any time in the last century or few centuries on the moon. So it's interesting, but it doesn't necessarily explain TLP. And just to highlight a bit more about the dust, this is an image from the moon's surface taken in the 1960s by the Surveyor 7 spacecraft. And this, I believe, is before sunrise, and it's showing a glow on the horizon. Now, at first they thought it was due to diffraction of sunlight over the horizon, but later studies showed that this is due to a dust layer just a few centimeters above the moon's surface on the horizon, and it's just forward scattering the light towards the camera. So the sun is beneath the horizon and the dust particles are sending that light, which they are, illuminated towards the camera. So electrostatic levitation dust particles definitely occurs on the moon. It's been replicated in laboratories. It was even detected by the Lunokhod, that's a Soviet rover, which carried a photometer and picked up a light glow didn't get pictures like this, but it picked up a light glow in the morning. And Apollo instruments, which were supposed to be looking for debris from meteorite impacts, again got swamped by dust particles at sunrise and sunset. This is a sketch made by one of the Apollo astronauts orbiting the moon 100 kilometers up, and before sunrise they picked up the solar corona, but they also picked up a glow very close to the horizon. There's still some contention over this. Some people say it's zodiacal light. A spacecraft flown by NASA looking for this thing in the moon's exosphere or atmosphere looked for many months a few years ago and couldn't find anything, but it was at a time of solar minimum, perhaps when there weren't many charged particles. It could also be there was a meteorite impact and you're picking up dust in the lunar exosphere around there. But it's a puzzle. We haven't really fathomed out what the astronauts saw. This slide just shows you the locations on the moon of deep quakes. Now remember, they are very quiet quakes, about sort of magnitude 1 or less, and there's lots of them, and they're often related to tidal stresses from the Earth because they occur at some perigee and apogee. But it also shows the locations of some more violent shallow quakes, which hypothetically might release any volatiles underneath the surface, which could perhaps cause some dust particles to be levitated. It's very speculative, but it does show that these things occur. So the minority of quakes occurring on the moon are shallow quakes, just a few a year, and they are typically magnitude 2 to 4, but geological evidence shows that they may be very occasionally 5 to 6. In terms of geological evidence for tectonic activity on the moon, if you look at wrinkle ridges on the moon's near side, where there's been a bit of buckling due to stresses as the moon's surface cools and contracts, it shrinks, and you get these wrinkle ridges, and you also get things called lobate scarps where there's been a contraction in radius. You see a lot of fresh boulders like that. Now they have a finite lifetime on the moon because they get hit by micrometeoroids or slightly big meteoroids and basically get smashed to pieces and become more like that. So this indicates some recent geological activity in the last few million years. NASA's Lunar Reconnaissance Orbiter has photographed the lunar surface under similar illumination, takes one picture and then another picture where the illumination is similar and divides one into the other, and you can see from this that it shows up occasionally interesting things like this landslide. More often than not it will detect a new crater, but on this occasion it's picked up a landslide. And that, looking at the size of that, that's 600 meters across there, that could in theory be detected from Earth-based telescopes. We're only talking about, what, about 2 kilometers for the length of that thing. It might be possible to detect changes on the moon like that. And Russian planetary geologist Sasha Bazalevsky has pointed out there are fault scarps on the moon's polar regions and elsewhere too, but he's particularly interested in the polar regions, which could be activated by the shallow quakes, and as you know, the moon's polar regions have a lot of frozen volatiles and these could be released. So it is a way of producing gas on the moon's surface. Now, one thing which appeared in the TOP catalogue on a few occasions in the past has been a single flash of light seen on the moon, as I explained with the Leon Stewart flash and that one seen at the end of the Second World War. But now we have video evidence of these. So on the left hand side over here we have a first impact flash detected from the UK. I won't say discovered, but detected from the UK, from Aberyswyth on January the 1st 2017, and it shows, these are slowed down of course, it shows the impact flash over there. This was actually discovered from Switzerland, and I checked my video a few months later and it was confirmed on that. We also have video from Italy as well confirming this, and it's a kind of interesting flash. Normally they're point-like, but sometimes they can have distinct shapes to them, possibly due to the way the ejecta cloud is going out. This over here is from NASA's Lunar Reconnaissance Orbiter images, before and after, picture of a new crater on the moon. This was seen from Spain, impact flash seen from Spain. It was a very bright one, lasted several seconds, and that's the resulting crater that formed. So at least we know that this type of TLP, a single flash on the moon, we can explain a lot of these away now as impact flashes. Although I haven't talked about the frequency of TLP, I have done some statistics on this, and they are incredibly rare. If you divide the number of TLP by the number of hours people have put in looking at the moon anyway, you typically see a TLP, perhaps a reliable one, perhaps once every few hundred hours. So they are incredibly rare. It's not the sort of thing you're going to go out and see all the time on the moon. Anyway, because of that, the policy we have in the BA lunar section and the Association Lunar and Planetary Observers lunar section is not to actively go out looking for TLP, but to try and disprove past TLP by getting people to look again when the illumination on the moon is within about plus or minus half a degree of what it was when the TLP was originally seen. This way we're seeing the normal appearance of the surface, and from that we can judge what in the past what the observer saw, whether it was a normal appearance or something unusual. If you can't figure it out, we can take images produced now and we can simulate atmospheric spectral dispersion, color or chromatic aberration, atmospheric blurring due to the seeing conditions, to see if we can simulate what was what the observer saw. We can also get people to look at when the libration, that is the geometry of the moon as seen from the Earth, was the same as well. Now this is a lot rarer, getting the illumination and the geometry view the same, but nevertheless we do have that capability as well to look at those particular times. So that's what we like to encourage observers to do. Although I could show you 3 examples of TLP we've managed to disprove in the past, I've condensed this into one for the moment. So if we've skipped a couple of slides here. This is a TLP report from 1992 by David Darling, who used to run the TLP section at ALPO. A very skilled observer. He drew what he saw, and on this occasion, 1992 October the 21st, he saw the crater Tycho and what looked like a pearl necklace, a V-shaped pearl necklace coming off of the central peak, which looked very unusual. And it's worth reporting that as a TLP. It does look strange. But we found with repeat illumination observations, as you can see over here, in fact it turns out to be just a natural effect, just highlands starting to project through. So I'll just move on to the next slide. Yeah, this is a picture taken by Bob O'Connell, American ALPO observer in 2012. Again, it shows this V-shaped formation here, which explains this very, very well. So it just shows the power of repeating your observations when the illumination is within about plus or minus half a degree. Half a degree is very, very small. It's just the diameter of the sun. You can sometimes replicate these effects, and then we can remove this TLP from the database. So how do you go about observing? You can use pretty much any size telescope, obviously the bigger the better. You can observe visually with a CCD camera, but when to observe? We have this website over here, hosted by the University of Aberystwyth here in the UK. It's called Lunar Schedule, and for each month, for different locations on the Earth's surface, just find the one which is nearest to you. It'll tell you for a particular day what we want you to observe, and sometimes why and what to look out for. Okay, now if there isn't much to see, there's a web link on there which is for repeat illumination predictions, a little bit more detailed, and that'll give you a lot more choice, but this is one we'd like you to focus on. If there are any TLP seen, like I said, they are incredibly rare. If you click on this Twitter account over here for Lunarnaut, that will send you the list of the current news of what TLPs have been reported, or more likely impact flashes, because a lot more people are observing those now. Okay, thank you very much for listening, and I'm sorry this is all in English and not in Spanish. If you have any questions, then please feel free to email me at atc@aba.ac.uk. Have a great day. Thanks.
Muy bien, amigas y amigos de la Sociedad Lunar, muchísimas gracias por haber estado con nosotros y por supuesto muchísimas gracias a Tony Cook por haber compartido esta charla tan interesante. No es un material que sea tan común encontrar, mucho menos en castellano. Creemos haber hecho una contribución al campo de esta temática, y recuerden que nos vemos mañana a las 19 horas para hacer una observación lunar en directo por este mismo canal en YouTube. Muchísimas gracias, hasta pronto.